Let's begin with our second talk for today. It's Pandit from ICST, and he's going to tell us about Calabi-Yau structures and spherical functors.
Thanks a lot, Tony. It's really great to be here. And so one of my experiences of doing mathematics for the last several years has been that all roads lead to Fukaya categories. So whatever I do, it ends up being secretly about Fukaya categories. And even without being an expert on Fukaya categories, I have to say that it's always like been a powerful organizational way to think about things that has influenced me a lot. So it gives me great pleasure to be here at the conference in honor of Fukaya. Happy birthday, Kenji. So my talk will be in some sense about Fukaya categories, but from a more categorical perspective. So to situate ourselves, we've seen this already earlier this week. We're interested in the sort of situation where we're interested in some space X, and we're interested in computing some sort of invariance or something about the space. And one of the tested and tried methods to do this is to fiber this over something lower dimensional. And you might try to compute the invariant of X in terms of some invariant of B with coefficients somehow in the fibers of X. So, for example, you might compute the cohomology of X as the cohomology of B with coefficients in some local system, where the fibers of the local system are the cohomology of the fibers. And so what we want to do here is some generalization of that. So Maxime has advocated this idea that you should study Fukaya categories of higher dimensional manifolds. So let's say this is a symplectic vibration. We want to study the Fukaya category of X in terms of some data on B and express. So I'll write f of X for the Fukaya category. And we'd like to have something like this, that the Fukaya category of X is Fukaya of B with coefficients in something I'll write S. So this S will be some sheaf of categories. And a more technical term for that would be a Pervers-Schober, specific kind of sheaves that we want to look at. And the rough idea is that if I'm looking at a point in the base where the fiber is smooth, then the stalk of the sheaf S sub X should be just f of the fiber, if this is smooth. Right. So there are many things you can do with this sort of approach. If this sheaf theoretic approach, you can try to construct various structures on, well, the first thing would be to prove that something like this is true, but even suppose we don't have this equivalence, we can just take the right-hand side to be our definition of whatever this category is, and we can ask whether we can construct various structures on this category starting from data on the stalks of the sheaf of categories. So we've already heard earlier this week about how you might try to construct stability conditions on this Fukaya category by starting with the data of stability conditions on the stalks of such a sheaf. And today I want to talk about constructing Calabi-Yau structures. So maybe let me just start by drawing. Okay, I'll just state the goal. So the goal, one goal would be to construct Calabi-Yau structures on f of Bs, or equivalently on f of X, starting from with the data of a Calabi-Yau structure, which I have to define what that means, a Calabi-Yau structure on S. Okay, so part of the problem will be to say what a Calabi-Yau structure on S is, and then to say how you can use a local to global principle to construct a Calabi-Yau structure on the global sections. Okay, so whatever this will be, it should roughly consist of the following thing. So let's say I'm in a situation where the fibers are compact. So the smooth fibers are compact manifolds in the Fukaya category of a smooth of a compact manifold should be a Calabi-Yau category. So one of the things I'd like to axiomatize here is to say that if I look at the stock over a smooth point, so this should have been S sub B. If the fiber is smooth, then I should have a Calabi-Yau structure on that point. Okay. Plus some data at the singularity. So let me say what I mean. So here's a picture of what we're looking at. We have some. Let me specialize. So let's go to the case where the dimension of B is 2. And in fact, let me take B equal to the complex plane with some mark point at infinity. You can put in more mark points, but I'll just start with one mark point. So you have some picture like this. You have some singular fibers in X, and this maps down to C. And in here I have some special points which correspond to the singular fibers. And near these special points, I have a local picture where I have just one singular fiber. And I can associate to that setting what I might call the local Fukaya-Seidel category, whose objects will be vanishing cycles, vanishing sort of thimbles that end in this here. So let me visualize this by saying that I draw a graph to make contact with Carlos's talk, for example, from earlier this week. So we have the complex plane, and we're looking at the Fukaya-Seidel category of the space X equipped with this potential. So my map pi renamed it W to suggest you want to think of this as a superpotential. And the objects in this Fukaya category are some Lagrangians, which at infinity are supposed to lie over the ray that goes off to infinity. But I can also look at a small disk and look at the local Fukaya-Seidel category, which is Lagrangians, which in some compact set do whatever they want, and then asymptotically they lie along this ray. So that's the situation. And let me draw a bigger picture of the same thing. So let me draw a picture of this graph. So what I'm supposed to associate, and this graph can do something bizarre on the right. There can be lots of more edges and vertices, but just looking at this local picture, well, to this vertex I have some category xi, which is the local Fukaya-Seidel category at this vertex. It's called x, little xi. And as I'll explain in a second, you expect to have some functors. So at each of these I have such a category, xi, xj, and so on. And over a generic point, a smooth point, I have the Fukaya category of a smooth fiber, which is some fixed category which I denote y. So over some smooth point, we have a copy of y, which is the Fukaya category of a smooth fiber. And I'll argue in a second that we should have functors which map xi into y. So I'll put a copy of y here. These functors are basically, if I imagine an object here to be some sort of Lagrangian that vanishes at this point in this fiber, then I'm just taking the fiber of, I'm just slicing that by taking the fiber over some point. That gives me an object in the Fukaya category of the fiber, and that gives me a functor from xi to y. Now, what should I attach to this point here? So at every smooth point I have a copy of the category y, but at this point I should attach some category. And what it should be is basically looking at a small open neighborhood of this. I'd like to attach the Fukaya category of the inverse image of this, where the Lagrangians are supposed to asymptotically live over these edges. And I can describe that by saying I put a copy of Y tensor representations of AN if there are n plus 1 vertices here. Sorry, edges. And I have functors that go from representations, I have functors from representations of AN to n plus 1 copies of representations of A1, which give me maps by just restricting to the various vertices of my quiver, and those give me a bunch of functors from this category here into Y by just tensoring that with Y. So I have a category sitting here, and I have a bunch of functors onto each edge, and at these special vertices, the singular vertices, I have functors from these special categories xi that have attached to each singular vertex into the general category Y. So what is the Fukaya category of the whole thing supposed to be? It's supposed to be, so I have this graph gamma. And really, the Fukaya category of this graph with respect to this, okay, so maybe I should just say this. So the data of, so Kapranov and Schickman axiomatized, or they said, they gave an explicit presentation for what this perverse sheaf of categories should be. And in this specific case, giving a perverse sheaf of categories amounts to the following data. It amounts to giving this category Y, and giving, for each of the singular points, which I declare to be singular points, a functor from, a spherical functor from xi into Y. So let's say what a spherical functor is. So I give a bunch of functors from these categories xi into Y. And that is the data defining my sheaf. Because outside of these singular points, Y is a local system of categories. In this case, I'll just take it to be, yeah, I mean, so strictly speaking, these Ys are all different Ys, but they're canonically identified because you have a local system. Okay. Right. Yeah, so now I want to define the Fukaya category of this graph with coefficients in this show. And that's going to be the limit of the diagram of categories that I drew in the previous blackboard. So I have here a diagram of categories, and the limit of that is what the Fukaya category of this graph is going to be. And this is basically an iterated homotopy pullback. Because the shape of the diagram is such that I'm at each stage I'm just taking, for instance, here I'm taking the pullback of xi mapping to y, and this y tensor rep an mapping to y, take the pullback and then iterate that procedure. Right? So this is a very special kind of diagram, and the limit is an iterated pullback. So in order to construct a Calabi-Yau structure on this category F of gamma S, I should tell you I already have a Calabi-Yau structure on Y, and I should put some additional data which is compatible with pullbacks in some sense. So let me explain what that is. So let's say a CY structure, a Calabi-Yau structure. And make this more precise as we go along. So the Calabi-Yau structure on S will be a Calabi-Yau structure on Y, and a relative Calabi-Yau structure on each of the functors xi mapping to Y. So that would be the data, and I claim that if you have such a data, which I have to define precisely, then on the global sections, which I defined by that formula, I will inherit a Calabi-Yau structure canonically. Right. So what will be the strategy of the proof? It will consist of maybe let me state the theorem, and then so the theorem will be that if S is equipped with a CY structure, and I'm being a little vague here, so I'll be more precise soon. If S is equipped with a CY structure, then the natural map from F of gamma S into Y, product of Y, one copy of Y for each outgoing vertex of the graph. So in this picture, I have exactly one outgoing vertex to my graph. You could imagine having more of them. These points are not outgoing vertices. The special singular points are not outgoing vertices. So this functor carries a relative CY structure. In particular, if there are no outgoing vertices, if I'm just connecting two singular points, then I get an honest Calabi-Yau structure. So maybe also a comment or remark is that a CY structure, a relative CY structure of dimension t on a functor x f to y will be the same thing, on a functor to 0, where I think of 0 as a d-dimensional Calabi-Yau, will be the same thing as a t plus 1 CY structure on x. So in particular, if I didn't have any outgoing vertices, I would have just produced a Calabi-Yau structure. Okay, so what is the strategy? Are there any questions at this point? Okay, so I'm not going to tell you what, before I tell you what this relative Calabi-Yau structure actually is, let me tell you how what the statement of the pullback, the behavior of this thing on the pullback is. Right, so the theorem and I should say that all of these things are probably well known by many experts, and many of these ideas go back to work of Conservation Solomon, Conservation Vasopoulos, Ginsberg, and various other people. It also involves ideas of Antefin, Bakier, and Letzozi, and Kalak on shifted symplectic structures. And there's probably a big list of people I left out there, so it's not intentional. This is just our attempt to understand some of these ideas. So here's our formulation of how to think about this. So if I have a diagram of categories, and let me give these guys some names, which might be useful later. Suppose I have a diagram of categories like this, and let me assume that this is a pullback square. So I make the following assumptions. The upper square, upper left square is the pullback. And when I say pullback, then all my constructions are in the infinity categorical world, so everything is homotopy, pullback, and so on. So assume the following. Assume the upper left square is a pullback. U mapping to x cross y. And I'm going to write x bar to suggest that you should think of this map as being like a cobordism from x to y. And I'm going to reverse the orientation on x, the orientation being the Calabi-Yau structure. So I'll explain what it means to reverse that, but you can ignore that for the moment. So assume that u going to x cross y and V going to Y cross Z carry relative Calabi-Yau structures. Then the induced map, by composing these two cobordisms, which is the map from W to X bar cross Z, carries a relative Calabi-Yau structure. So now it should be clear how to construct this Calabi-Yau structure on this global sections along the graph, which is given by this iterated pullback, the homotopy limit of this diagram of categories. So you need two things. You need to know that each of these functors has a relative Calabi-Yau structure, which was part of the definition of a Calabi-Yau structure on the Schober. And you also need to know that this guy, Y tensor FAN, mapping into each of these guys carries a relative Calabi-Yau structure. So the idea, the proof of, what was the theorem? Maybe this is theorem 1. 2 should be maybe a proposition or something. Proposition 2. So the proof, so sketch of proof of theorem 1. You use the fact that, so you do a computation which says that representations of AN mapping to that A1 tensor plus 1 times carries a natural relative Calabi-Yau structure. And I just want to comment that this actually fits into the general framework of what I just said, that if you have the Fukaya-Seidel category and the Fukaya category, then you have a natural functor from the Fukaya-Seidel category to the Fukaya of the fiber. And this is a special case of that, where I'm just doing Fukaya-Seidel of a disk with marked points, the Fukaya category of the disk with marked points, which you can think of as the Fukaya-Seidel category of the Landau-Ginzburg model with the potential at the end. And this is just the map to the Fukaya of the fiber. So this carries a natural CY structure, and then you just show that if X, so maybe it's a lemma, if X to Y carries a relative CY structure, and Z is any category, then X when I say any, I'll have some technical condition on them. All my categories will be locally proper, but it's not particularly important. Then X tensor Z mapping to Y tensor Z also carries. So that implies in particular that this Y tensor FAN mapping to these n plus 1 copies of Y has a relative Calabi-Yau structure. And by the definition of a Calabi-Yau Schober, each of these functors has a relative Calabi-Yau structure. So I'm in the situation of my theorem. All the iterated pullbacks that I perform when I compute these global sections are of this type. And I can apply the theorem. So now you simply apply the theorem and you get the results. So are there any questions about the structure of the proof? Because next now I want to actually define what a Calabi-Yau structure is. Right, so use we should put these numbers 1, 2, 1 plus 2 plus proposition implies the theorem. Okay, so what is a Calabi-Yau structure? It's a generalization of a fundamental class on a compact manifold. I'll try to make that more precise. So let's start with let A be some A infinity, so this section is Calabi-Yau structures. So let A be some A infinity algebra. If you prefer to think of it that way, E1 algebra. So what is an A infinity algebra? You can think of it in the following way. You can think of it as a functor. A is really a functor from the category of 1 disks. Into some symmetric monoidal category, which typically you take C. When we talk about A infinity algebras and chain complexes, we take C equals chain K. Chain complexes over K. Right. So what is the actual algebra? The algebra itself is what I assign to, I have to tell you what this category disk 1 is. So in general, disk N is a category whose objects are just natural numbers, are labeled by natural numbers, and maps from N to N, or not N because I use N here, so maps from K to L is embeddings of disjoint union of K copies of Rn into disjoint union of L copies of Rn. So this is just another way to describe the N disks operand as a category. And saying that I have a symmetric monoidal functor from this category into C is saying that I have an algebra over this operand. So really what we call A by abuse of notation is just A of R. So if I have such a functor, which is an E1 algebra, I can do, there's a very natural thing I can do. Well, the category where the objects are Rn sits inside a bigger category, which is the category of N manifolds. In particular, R sits inside the category of 1 manifolds. So I can Kahn extend this functor. To the category of 1 manifolds. I'll let the integral over A. This is the left Kahn extension. Which basically means that one way to compute it is to say that if I'm given a 1 manifold, I look at all possible configurations of copies of R sitting inside that 1 manifold, and to each such configuration I attach a copy of A to the A tensor as many copies of R as I have, and I take the co-limit over all those. So I integrate out over all possible configurations. So since we're doing 1 manifolds, there aren't very many interesting 1 manifolds. There's essentially only one interesting compact 1 manifold. So you might ask, what is the value of integral of A over S1? It has a name and it's called the Hochschild homology of A. This way of presenting it makes manifest the fact that this carries a circle action. So this carries a circle action. So this carries a circle action. And the functoriality of the extension tells me that I have a natural map from the integral over S0 cross I of A into integral of A, S1A. So this thing is equivalent to A tensor A. And this thing is the Hochschild homology of A. It's called the natural map here. And what a Calabi-Yau structure is a map, is an S1 equivariant map. So the data, so being S1 equivalent is not a condition, but it's extra data since I'm working in a homotopic kinetic setting. So it's a map, if you like, from here to here, here to here, to K shifted by minus T. So map with X1, map, let me emphasize that it's a map with S1 equivariance data, S1 equivariant structure. Another way of saying that it has an S1 equivariant structure is to say that this map factors through cyclic homology, which is a tautology because cyclic homology is the orbits of S1 acting on Hochschild homology. So a Calabi-Yau structure will be such a map from Hochschild homology, from the factorization homology as this integral is called, over S1 into K shifted by minus D, with a non-degeneracy property. So this definition is due to Kontsevich-Solomon, I think. So sigma is above is a CY structure of dimension D. If A tensor A mapping, was that A tensor A mapping to K shifted by minus D is non-determinate. Right, so this is a kind of Poincare duality, right? So let me say what that is in terms, since I was using the language of categories instead of algebras. I mean, you can pass between algebras and categories by taking modules over the algebra, and in other direction by choosing a compact generator. But let me say what this means if I want to think of it in terms of categories. If Y is some category means always means K linear stable infinity category or A infinity category. And I assume that which is locally proper. So assume Y is locally proper, which means maps from X to Y, but any two objects in Y is in perp. Okay. So actually there's a version of all of this for smooth categories and so on, but it's much more intuitive for proper categories. That's why I'm talking about proper ones. Okay, so then what does this really mean? What does this translate to in that language? That means that I have a map. So maybe let me write that. A Calabi-Yau structure would be a map CY structure of dimension D is a map, is an S1, is a, maybe I want to say weak and strong here. So let me say a weak respectively strong. CY structure dimension D is a map, respectively a map with S1 equivalence data from the Hochschild chains. When I say Hochschild homology, I mean the spectrum of the chains computing Hochschild homology. Map from HH of Y to K shifted by minus D, such that for any you have a non-degeneracy condition, and the non-degeneracy condition is the following: that if you look at maps from X to Y, tensor maps from Y to X, you can multiply and get into maps from Y to Y. Then you can take the bulk boundary map, or whatever you like to call it, into Hochschild homology of Y, and compose the Calabi-Yau structure to get into K shifted by minus D, and you want this composite to be a non-degenerate pairing for every X and Y. So that's what a Calabi-Yau structure is. Of course, we know lots of examples of these. If you have a Calabi-Yau manifold that carries a natural Calabi-Yau structure, which is given by the volume form and so on.
What is the reason if you have Calabi-Yau, right? You have a finite field.
Do you have Calabi-Yau structure?
Does it have a strong Calabi-Yau structure?
Or finite field? I don't know.
Or positive electricity, yeah.
That's a good question. Yeah, never really thought of it. there'll be tricky issues with the Bookshell homology and so on.
Yeah.
Because Bookshell cosine doesn't work.
It's not a solution.
Yeah. Right. Okay, so now I want to define what a relative Calabi-Yau structure is. So all of this stuff should have reminded you of Poincare duality in the sense that if I have X on compact manifold, and I can look at a cup product composed with integration against the fundamental flux. And this thing is not integral. But now you can ask, so if this X is a closed manifold, you have this story. In fact, more precisely, it will translate into the statement that the local systems, the derived category of local systems on X is a Calabi-Yau category in this sense. But now I can ask what happens if I have a manifold of boundary, which Jan already talked about. In fact, Jan talked about manifolds with corners and Calabi-Yau categories with corners. Yeah. So in this situation, you can ask, what is the analog of Poincare duality, or what is the analog of a Calabi-Yau structure? So that's what I want to define next. So if definition is if f from x to y is some functor, so all categories are locally proper. Maybe I should henceforth, unless I specify. So all categories locally proper. Make a definition. If f from x to y is a functor, and y carries Calabi-Yau structure of dimension d, then I'm going to define what a relative Calabi-Yau structure is. It consists of two pieces of data, or one piece of data and one condition. Then an isotropy structure, and this is modeled after Antep-Toen Bakiewicz's definition of Lagrangian in a shifted symplectic stack. If you're familiar with that. An isotropy structure is a diagram, is a homotopy commutative diagram. HH of x mapping to HH of y, mapping by the Calabi-Yau structurization to minus d. So it's data because it's not just saying that this diagram commutes. Saying the diagram commutes is providing a two cell that makes this diagram commute. So it's the data of that two cell. And as soon as you have certain.
I can change once. It's in corners, it's not using to map it to K minus D.
Yeah. So the cone includes the data of a homotopy commutative sphere, which when you have this isotropy data, you get a nice big diagram, which I'll draw. I don't know if it will fit in one slide, let's see. So then for all x, y, I have this big diagram I can draw. I have maps in x from x to y, tensor maps in x from y to x. And I can map this by doing f tensor identity to maps in y from fx to fy, tensor maps in x from y to x. Then I can do identity tensor f, get into maps in y from fx to fy, tensor maps in y from fy to fx. Sorry, the last bit is non-legible. I hope it's clear from this bit. Here I just take the identity map, the same thing. And then I multiply and get into maps from y to y in x. Here I multiply and get into maps from fx, which is maps from x to x. Maps from fx to fx. And I have a map f here. Then I can go into the Hochschild homology by the boundary map. Here I go into the Hochschild homology of y. So all of these diagrams commute. The first diagram just commutes because multiplication is, I guess multiplication is associative. The second diagram commutes because f is a functor. The third diagram is just the functoriality of this bulk boundary map. And finally, I have the isotropy data. So I have a 2 cell here, a 2 cell here, a 2 cell here, and a 2 cell here. All of this makes this big thing a homotopy commutative diagram. And I'm interested in the outer portion of this diagram. By adjunction, the outer portion of this diagram gives me a picture like this. Gives me a homotopy commutative square, maps from x to y in x, maps to maps in y from fx to fy, maps to maps in y, sorry, maps in x from y to x. And now I should have a dual and a shift by minus d. So I get a square like this. And the non-degeneracy condition is that this should be a homotopy pullback square. Pullback or push out is irrelevant because we're in spectra, so it's pullback squares are the same as push out squares. So that's the definition. So relative Calabi-Yau structure is an isotropy data, which is for which this diagram is a pullback square. So a relative CY structure on f from x to y is isotropy data satisfying non-degeneracy. Okay. So now it's not very hard to see how to prove theorem 1. So let me sketch the proof of theorem 1. Theorem 1 said that I had a pullback diagram. W, I should get back to my symbols, get the symbols right. Yeah. W goes to U, goes to X, goes to Y. So now I can say in words what it means to take the opposite of a Calabi-Yau structure. It just means that I take minus sigma instead of sigma. Okay. And so if I have a diagram like this, I'd like to produce and if I have relative Calabi-Yau structures on U mapping to X cross Y and W mapping to Y cross Z, I'd like to produce a relative Calabi-Yau structure on W mapping to X cross Z. And so the first thing I have to do is to produce isotropy data and show that it's non-degenerate. So the isotropy data is very easy. You simply apply Hochschild homology to this diagram and you get a diagram. So I should say there's going to be no deep mathematics here. It's all triviality, but it's just a question of writing down the right definitions. So you have this diagram. This part is just writing down HH of this thing. And now I can use the Calabi-Yau structures here. So I get maps into K shifted by minus D. So this will be sigma y. This will be minus sigma x. Because I took the opposite orientation. This will be minus sigma y. This will be sigma z. This will be minus d. And the identity maps. So this whole square is homotopy commutative for obvious reasons, because each of the pieces was homotopy commutative. These are homotopy commutative because sigma y minus sigma x, I mean u mapping to x cross y is supposed to be relative Calabi-Yau for sigma y comma sigma minus sigma x. So this is homotopy commutative by the isotropy data on u mapping to x cross y, and similarly for that square, this square is trivially homotopy commutative, and the top left square is homotopy commutative because h is functorial. So we have this big square, so this gives isotropy data on w mapping to x bar cross z. I need to check that this is non-degenerate. First time do that. So non-degeneracy is also, you similarly just apply, it's a statement about mapping spaces in all these categories, so you apply map blank blank to this diagram. And roughly speaking, since taking mapping spaces is like mapping an interval into your category, and maps commute with limits, taking map of blank of something into something blank is a functor that commutes with limits. You get a similar diagram of mapping spaces. So you have maps of uv in W going to maps of h prime u h prime v in what was it u goes to maps in x of f prime h prime u f prime h prime v and so on. This is now in V. This is equals to so the upper left corner is obvious. Here I'm using the non-degeneracy of the triangles that come from non-degeneracy of the individual Calabi-Yau structures to construct this square, and then this continues from here to maps in W of V dual shifted by D, maps in V prime V H. This is simply what you get by the upper left part of this diagram is just taking mapping spaces in these categories and applying these various functors. So these guys were h double prime, h prime, g double prime, g prime, f double prime. And the lower left part comes from using the commutative square that I described over there for the non-degeneracy data. So you can check just by abstract nonsense that all these squares are homotopy commutative from the data that already exists. And so u mapping to x cross y and v, y mapping to, what is it? V mapping to y cross z are relative Calabi-Yau. Gives non-degeneracy data here, which implies that all squares above are homotopy commutative. Are full-back squares. Full-back push-out squares. which implies the outer square all small squares are pulled back for short squares, which implies that the big outer square is also pulled back, which implies non-degeneracy for W mapping to x bar plus c. So it's really, there's nothing to it, it's just the definition and just playing around with some diagrams. So that's how you prove this result. Okay, so now I just want to finish by saying a few words about, so I told you how to glue these Calabi-Yau structures to produce a global Calabi-Yau structure. And the key assumption I put in there was that, if you go back to the picture with Schober's, we had some Schober, we had some picture where we had some singular points, and we had some categories xi sitting here, xj and so on. And we have functors from this guy, from each of these guys into the same smooth category y, right? So xi into y and so on. And in the definition of Schober, these categories, these functors are supposed to be spherical functors. So I'll define what that is in a moment. Schober is essentially going to give you a bunch of categories which you might want to think of as Fukaya-Seidel categories, and a bunch of functors to the Fukaya category of the smooth fiber, and these are supposed to be spherical functors. And in my axiomatization of what it meant to have a Calabi-Yau structure on a Schober, I required these spherical functors to carry relative Calabi-Yau structures. So you might ask, how can I reformulate that in terms of spherical functors? What does it mean to have a relative Calabi-Yau structure in the language of spherical functors? And it turns out to be quite a natural picture. So let me first say what a spherical functor is, and then I have about 8 minutes, so let me. So a spherical functor is some categorification of the notion of a perverse sheaf. So this was defined by Kapranov and Sheckman. So if you look at perverse sheaves on the disk, we know that this is the same thing as looking at a pair of vector spaces, V and W, with maps going back and forth between them, such that 1 minus alpha beta is invertible, and 1 minus beta alpha is invertible. 1. So a spherical functor is a categorification of this notion. So how do you categorify taking the difference? You take the cone. So f from x to y definition. And this definition, I think, is due to Anu and Pavlinenko. And maybe also Kontsevich, Kazako-Kontsevich Fanta, some version of this definition there. A functor f is spherical. So let's say you have a functor, and suppose f upper sheik is a right adjoint. To f. Okay. Sorry. Then f is spherical if you take the fiber T sub x, I guess, the fiber, homotopy fiber of one, the identity functor on right left, so mapping to f upper sheik f is invertible as a functor, and T sub y, which is the fiber, fiber of f upper sheik mapping to identity on y is invertible. So that's the definition. we can show that, so there's a proposition, Shano and Lovinenko, it says that 1 plus 2 is equivalent to 1 plus 2 prime, where 2 prime is the following condition, that f also admits a left adjoint. So maybe let me say that f, let me put it in here, that f over here admits left adjoint. And depending on which starting point you take, it would follow from the definition of. And the condition 2 prime says that if you look at the national map that goes from f upper shriek to f upper shriek times f prime, f star, which is given by the unit map, and compose it with the projection to t, what is it, tx shifted by 1 times f upper star, then this map should be an equivalence. In other words, the left and right adjoints are essentially equivalent up to the twist, where this twist is this fiber of this unit map.
So you just like to know that there is a similar condition, you call it one about all twists.
Yeah.
Any two imply
Yeah.
force.
Yeah, so in your paper there are 4 different conditions, and they're all, any 2 of those imply all the others. So I only need this one for this talk. Okay, so let me say what, here's our attempt to try and understand how to reformulate what a relative Calabi-Yau structure is in the language of this spherical functors. Okay. So let me just set t equal to tx shifted by 1. And suppose that y is Calabi-Yau of dimension d. Then compatibility, so I want to say what it means for a spherical functor to be compatible with the Calabi-Yau structure. So compatibility data is the following thing. It's an equivalence of t with the self functor on x shifted by minus d. This twist functor is identified with the self functor shifted by minus d. Let's call this alpha, such that the following diagram commutes, or rather, such as that there exists 2 self-witnessing homotopy commutativity of the following diagram of f upper star, f upper shriek goes to f upper shriek f upper star goes to t f upper star. That's what I already described. Goes to alpha, goes by alpha to the self functor of x to the minus d times f upper star. And over here I have that. So f upper shriek is canonically isomorphic. If you have a left and right adjoint, you can describe this. If you know one of the adjoints, you can describe the other. The self functors are intertwined the 2 adjoints. So this is just abstract nonsense with the definition of the self functor, that you have this equivalence of f upper shriek with sx times f upper star times sy inverse. But since y is Calabi-Yau, sy inverse is identified with the identity functor of closed shift, and so I have a national map here, and I want a 2 cell witnessing the commutativity of this diagram. So that's what a compatibility structure is. So here's the theorem. And this time, so I can just take the theorem and stop. So the theorem, f, I stated a bit vaguely, and you can ask me for the precise version. F that admits left and right adjoints is compatible and spherical, fx to y, and y Calabi-Yau is compatible spherical equivalent to saying that F carries a weak relative. And I should emphasize the weak relative Calabi-Yau structure. So essentially saying that you have a relative Calabi-Yau structure is some way of saying that the twist functor, which is the monodromy essentially, is the Serre functor. That's part of the data. But if you want all the higher S1 equivalence data that goes into a Calabi-Yau structure, you should somehow enhance this with some extra data, which I don't know at the moment what that is. But the first piece of data defining a relative Calabi-Yau structure on a spherical functor is essentially this condition, that the twist, the monodromy, is the Serre functor, which is known for Fukaya type categories. And there are lots of examples of these compatible spherical functors, so maybe do I have 2 minutes more? So let me just give you some examples of these guys. So if D, if Y, if X is Fano, and D contained in X is an anti-canonical, which is of course mirror to the situation about Fukaya categories that I've been talking about, then I upper star, let me call this A, then A upper star mapping perf X to perf D is compatible spherical and in fact carries a strong relative Calabi-Yau structure, which suggests that you can somehow promote the spherical data to something that encodes the strong Calabi-Yau structure. So this of course is mirror to the Fukaya category situation I already talked about, but there's another interesting example that I don't quite understand the mirror to so well, which is you look at, let now Y be a Calabi-Yau, smooth and proper variety, and let D in Y be any smooth divisor. And now instead of taking the pullback, I look at the push forward, I lower star, mapping perf D to perf Y is a compatible spherical functor.
You don't want general type condition on D?
No conditionality. And there's further evidence that in fact this carries a relative Calabi-Yau structure, which comes from another theorem. And the theorem is that if you look at the induced map on moduli stacks of objects, induced map, I lower star from the stack perf D to perf Y carries a Lagrangian structure in the sense of Panchatu and Vakil. Which would be true if you knew you had a relative Calabi-Yau structure. So there should be some relative Calabi-Yau structure here. We don't know how to see it directly, but you can easily check that this is compatible spherical functor. So one question that all this begs is how do you promote this way of thinking about compatible spherical functor to something that exactly corresponds to strong Calabi-Yau structures?
Thank you. Questions? Everybody's hungry? Well, let's thank Pandit again.